Swayam Prabha. Digital India. Educated India.
Hello, welcome to Module 6 of second week of our course on Introduction to Dynamical Models in Biology. In the last module, we have started discussion on phase plane analysis, and we have discussed how for a system of ODE, we can use null lines to identify the steady states, and also how can we show those steady states in a phase plane. Now remember, when we build a dynamical model, we are interested in multiple things of the system. One obvious issue is that we want to understand the existence of steady states and the behavior of those steady states, as well as we want to understand the dynamics of the system around the steady states. So, to understand the dynamics, in case of one-dimensional system, for example, when you have one single ODE, what we use is direction field. I have shown a direction field that we have discussed earlier here. So here I have only one ODE representing the rate of change of x with respect to time. So in a direction field, I have plotted time in the horizontal axis and the dependent variable x in the vertical axis. And then I divide this whole x versus t plane in equal grid points, equidistance grid point. And each of these grid point, what I do, I draw an arrow, and the slope of that arrow is equal to dx dt. And you can calculate dx dt at each of these points based on the value of t and x and the ODE given to you. Now, if I have a system of ODEs, that means I have more than one ODE because I have more than one dependent variable. Then how can I represent the dynamics of the system, dynamics of the dependent variable with respect to time in a two-dimensional space? That's what we will discuss today. And what we will use is actually we will use a phase plane. So if you remember, for a phase plane, suppose I have two variables, dependent variable x and y. That means I have two differential equations, one giving dx dt, another one is dy dt. So if I have two-dimensional system, two variables only, dependent variables, I can draw a phase plane with x in the horizontal axis, y in the vertical axis. You can swap them. There is no issues that x should be always in the horizontal axis. So I have drawn put x on the horizontal axis, y in the vertical axis. Now, we have discussed that I can draw null lines on this plane, and the intersection point of the null lines, for example, these yellow dots here, are actually the steady state. Now, in case of direction field, for one single dependent variable, we divide the plane in equidistance grid point, and at each grid point, I draw an arrow with a slope equal to the derivative. But here, we have x and y axis. So I cannot draw an arrow with a slope dx dt or dy dt. So how can I draw an arrow here, or I can put something to represent the dynamics of y and x with respect to time. Remember, my intention is to visualize the change in y and x with respect to time in this y and x plane. What we will draw here is rather, I will divide this whole y versus x plane, which is actually the phase plane, this phase plane, into equidistance grid, and at each grid point I will draw an arrow, and the slope of the arrow will be equal to dy dx, derivative of y with respect to x. That's what we will draw. So that will show how y is changing as x is changing. And as x will change with time, so y will also change with time. So that's how I can visualize the change in y and x in a xy plane. But the issue is, how can I calculate dy dx? Let us see with a particular example. We'll take the old example of predator prey. So I have two ODEs here because I have two dependent variables, one representing the prey, the other one representing the predator. So prey is x and predator is y. So I have dx dt equal to x minus xy. This is first ODE. Second ODE is dy dt is equal to xy minus y. It is a common system of ODE that we have discussed earlier for predator-prey models. So for this system, I want to draw the phase plane and I want to divide the phase plane in equidistance grid point, and at each of these grid point, I want to draw an arrow representing dy dx. So how can I calculate dy dx here? Let's see. So dy dx I can write is equal to dy dt into dt dx. Now dy dt you have already given from the original ODE, and I can inverse this dx dt to get dt dx. So what I get? I get xy minus y, this is this one, dy dt, into inverse of this one. So inverse of this one is here. So I have dy dx, which I calculated from dx dt and dy dt, because it's a combination of both the derivatives. So now let us take a particular point and calculate the value of dy dx at that point in this xy phase plane. So let us take a point 3, 3. I have shown these by a red dot here. 3 versus 3, y is 3, x is 3. Now use this value of 3, 3 to calculate dy dx. How can I calculate? Dy dx is equal to, as I have calculated, x into y minus y divided by x minus xy. So put the value of x and y here. Both x and y are 3. So on the numerator, I will have 3 into 3 minus 3 divided by 3 minus 3 into 3, and that gives me minus 1. That means I have to draw an arrow at this rate point which will have a slope of minus 1. So essentially I want to draw an arrow there with an angle 135 degree. So let us draw the arrow there. So I have drawn a small arrow, remember, without an arrowhead, with a slope which is equal to dy dx at that point, and the value of dy dx at that point was minus 1. So I have drawn the line representing the arrow. Now I have to decide the arrowhead. Will the arrow move towards the left upper corner, or the arrowhead will be on the other side? So how to decide the arrowhead position? Let us use some thumb rule to do that. What we can do? We can do like this. Suppose when dy dt is greater than 0 and dx dt is also greater than 0, that means with time both x and y will increase, and I will put an arrow like this pointing up right hand side. When dy dt is greater than 0, that means y is increasing with time, and dx dt is decreasing with time, that means dx dt is less than 0, then I can have an arrow like this. So y is increasing, x is decreasing. Remember, my plane, I have x in the horizontal axis, y in the vertical axis. When dy dt is less than 0 and dx dt is also less than 0, that means with time both y and x will decrease, so I can have arrow in this direction. When the fourth case comes, when dy dt is less than 0 but dx dt is greater than 0, then I can have arrow in this direction. That means x will increase in the horizontal axis, y will decrease in the vertical axis. So this is the thumb rule that we can use, and it's a very easy thumb rule. So let us go back to our point 3, 3 and calculate what will be the arrowhead direction. So at point 3, 3, dy dt is given by the ODE x into y minus y, that is 3 into 3 minus 3, that is 6. So 6 is greater than 0. dx dt is x minus x into y, that is 3 minus 3 into 3. So I get minus 6. So minus 6 is less than 0. So I have y positive, derivative positive, x derivative negative. That means my arrow will be in this direction, following this particular rule. When dy dt is greater than 0, dx dt is less than 0, arrow will be on the left upper corner direction. So let us put the arrow there. So I have got the arrow here. So this is how I can take a point on the phase plane x versus y plane and calculate the slope of an arrow there from dy dx, and then I can decide the direction of the arrowhead based on the values of dy dt and dx dt. So what I can do, I have the whole phase plane of x versus y, and I can divide them in equidistance grid point, and at each grid point I can draw the arrow using the rules that I have discussed just now. So that's what I have done here for this predator-prey model. I have x versus y. I have shown these colored lines are the null lines that we have discussed. The intersection point of the null lines are the yellow dots. Those are the steady states. And you can see the arrows here at equidistance grid point. Each of the arrow is representing dy dx. That is how y and x are changing with respect to time. As y is changing with respect to x, that gives an x change with respect to y. And the direction is based on whether y is decreasing or x is increasing, like that, as we have discussed just now the rules. So in this way, I have filled the whole space with arrows. Now what these arrows are telling me? These arrows are telling me the direction of evolution of the system. So let us see how I can understand the direction or evolution of the system from a phase plane analysis. So suppose the same plot I have drawn here, just the color has been changed. So I have x in the horizontal axis, y in the vertical axis, same predator-prey model ODEs, and this is my phase plane. So suppose I start at this position. This is the initial t equal to 0 position. So the value of x at that point is this one, near 4, and the value of y at this point is just around 0.5 or something. So the arrows are telling me that as the time will progress, the system, the x and y value will change along these arrows. Just like the direction field, I can connect the arrow one after another, and I can get the trajectory, that is the geometric representation of time evolution of both the variables in this phase plane. So if I start at this particular point at t equal to 0, I will follow this closed loop path and come back to the same position. You can start at another point here, and you will follow the arrows, and the arrows are telling me that I will follow a closed path like this. So the phase plane with these arrows is telling me that if I start from a particular position where both x and y values are positive, this is this quadrant, I will follow a closed path where x will increase and then y will also change, and essentially I will have x versus x and y oscillating values, right? Because x is increasing and then x is decreasing, so I will have an oscillation of x. Similarly, y is also increasing and y is again decreasing with time, so I will have oscillation of y. And that's what we have expected for a predator-prey model, as we have discussed earlier. Now, apart from this trajectory, there is another issue here. If you remember, these black dots shown here are nothing but intersection points of the null lines. So these are steady state. So this is one steady state, this is one steady state, this is another steady state. So let us look into the stability issue of steady states, these steady states. The first one, this one is 0, 0, this one is 0, 0. So if you look into this steady state, let us clean a bit so that I can understand how the steady states are behaving here. So if you look into this particular steady state at 0, 0, if I start here at a close point of 0, 0, my arrows on the direct phase plane is telling I will move away from 0, 0. If I start from here, I will again follow this trajectory and move away from 0, 0. If I start from here, obviously I will move away from 0, 0. And if I start here, I will move away from 0, 0 and follow this closed path. So that means this 0, 0 steady state is such that if you are there, you will stay there. But if you are slightly away from there, that means you are parted from that 0, 0, you will never come back to 0, 0. In 3 quadrants, this one, and this one, you will move away from 0, 0. That means this 0, 0 steady state is obviously unstable, and this type of steady state having this type of trajectory around it are called saddle point. I will discuss them separately, what we understand by saddle point. Let us look into the other steady state, this one. Here, if I start somewhere close to this point, this steady state, I will follow a closed loop. I will never reach the steady state, or I will not also move away from the steady state. Essentially, I am moving in a closed loop, giving rise to oscillation for x and y. So this steady state is called center type steady state. In this type of steady state, if you are there at the steady state, you will stay at that steady state for infinite period of time. Whereas if you slightly parter from it, you will start moving in a closed path around that steady state. So this is called center type steady state. We will discuss that also. So let us look into different types of trajectories in phase plane and the steady states corresponding to those. Remember, when we draw these arrows on a phase plane and show the dynamics of the system by trajectories around the steady state, we call it phase portrait. So let us start different examples of phase portraits. The one shown here is represented by these two ODEs, dx dt equal to minus x and dy dt is equal to minus 4 into y. I have just given an example. If you use the same rule of plotting x in the horizontal axis, y in the vertical axis, and then divide this xy plane in equidistance grid point and draw arrows there using the rules that we have discussed, you will get this type of picture. Let us see the null lines. I have one null line here, I have another null line here. So they have intersected at this yellow dot. So that is my steady state. Obviously, this ODE is a linear system. So I will have only one intersection point between the null lines and I have only one solution. And this is a homogeneous linear system as you don't have any constant term on the right hand side of the equation. So steady state solution is 0, 0. So this is my steady state solution 0, 0. If you look at the trajectory, you can see easily, if I start suppose from this point, I will follow this arrow and collapse at 0, 0. If I start from this point, I will move towards the 0, 0 and collapse at 0, 0. If I start from this point, I will move and collapse at 0, 0. So from all direction, if you start, from any quadrant position if you start, you will eventually reach the steady state at 0, 0 asymptotically. So that means this is a stable point, this is a stable steady state. And all the trajectories are converging there. So this steady state is sometimes called sink. So this is called sink node or stable node. I can have the opposite one also. That will be unstable. So look at this phase portrait here. This phase portrait is coming from the ODE dx dt equal to 2 into x plus y and dy dt is equal to 2x plus 2y. Just for an example, I have taken these ODEs. So for this system of ODE, if you draw the phase portrait, you get this type of figure. So again, the null lines are shown by these two colored lines, and their point of intersection is this steady state shown by yellow dot. If you observe carefully, if I start near this steady state, I will move away. If I start somewhere here near the steady state, I will move away. If I start somewhere here, I will eventually move away. So you can easily see by observing these trajectories here that if you are at this steady state, at the intersection point of two null lines, you will stay there. But if you perturb the system slightly, the system will diverge away. It will move away asymptotically from this steady state. So this type of steady state is unstable, and it is like a source. It's from where all the trajectories are originating. That's why this type of steady state are called source node or unstable node. Let us look into few more examples. Here comes the saddle point. This system of ODE, that is dx dt equal to y and dy dt equal to 2x minus y, gives rise to this phase portrait. Again, these two colored lines are null lines, and these arrows here represent the slope dy dx. And as you can see, there are two paths through which you can actually reach towards x, the 0, 0 steady state position, whereas there are another path which diverge away from it. And in between these two paths, all paths will take you, if you start from here for example, it will take you towards the steady state, and then it will take you away from the steady state. If you start suppose somewhere here, you will go close to steady state, and again you will move away from the steady state. What I am doing, I am taking an initial point and then following the trajectory, the arrows to draw the trajectory. So if I start from this position, the arrows are telling me I will go towards the steady state and then diverge away. So the same thing is here. So in this phase portrait, we have a steady state, and there are only one path from both the direction from which, following this path, you can reach the steady state. But for others, either you will move away directly from the steady state, or initially you will move close to the steady state and then diverge. So these type of steady states are called saddle point, and obviously they are not stable. Let us look into the center type or the closed path type that we have faced earlier in case of predictor-prey model. Here I have taken a system of ODE, simple one, dx dt equal to minus y and dy dt equal to x. This system of ODE gives rise to this phase portrait. Again, these colored lines are the null lines, and the arrows represent dy dx. As you can see, if you stay at this yellow steady state position, you will stay there. But if I slightly disturb the part of the system, then there is a closed path through which the x and y value will keep on changing. That's true from here also. If I start from here, I will follow this path, and something like this, I will keep on moving. So I will have a closed path. Here this closed path looks like ellipse. It may have a different shape also, but I have a closed path. So in this case, the steady state is obviously unstable. If you move away from it, you don't have any stability. You do not go back to that. But if you are slightly away from it, you are in a closed path. So that's why it is called centered type. Now comes another type of phase portrait. I have taken two ODEs, dx dt equal to minus x plus y and dy dt equal to minus x minus y. These two ODEs is represented by this phase portrait. Again, I have two null lines here by the colored line, and the arrows represent dy dx. And the intersection point on null lines is the yellow dot, which is showing the steady state. If you start from anywhere, suppose here on this phase plot, and then the arrows tells you that you will follow this one, this path, and collapse at steady state. If you start from here, you will follow this path and collapse at steady state. If you start from here, you will follow this path and collapse at steady state. And notice the path. These paths are spiral type path. So if you start from a particular position on the phase plane, you spiral and move in spiral, and then the system collapses at the steady state. So obviously this steady state is stable because it is sucking everything towards it. If you are at that steady state, you will stay at that steady state. But if you are disturbed from this steady state, you will be following the spiral trajectory. With time, you will again collapse to that steady state. So this is a stable spiral or spiral sink. What happens if you have an opposite one? Let us take an example. So I have a ODE dx dt equal to x minus y and dy dt equal to x plus y. These two ODE give rise to this phase portrait. Again, these two colored lines are null lines and the intersection point is the steady state. In the earlier case, the trajectories were collapsing at the steady state. But look into this plot. Here, the arrows are moving away from the steady state. So if I am at steady state and if I get disturbed, suppose disturbed up to here, then the system will not go back to the steady state, but it will follow a spiral curved path and diverge away. Similarly, if we disturb the system and then release it, the system will move away in this direction. If I disturb part of the system from steady state and bring it here, and then it will diverge. So if I start from a initial value here, I will follow this path. So no path is going back and converging at the steady state. If you are at the steady state, if the system is at the steady state, it will stay there. If you disturb the steady state, it will diverge away from the steady state in a spiral path. So that's why it is called unstable spiral or spiral source from which all the trajectories are originating. So what I have discussed till now is different types of common phase portrait that you can expect. Both some of them are stable, some of them are unstable. For example, I have discussed stable node, unstable node. I have discussed stable spiral, unstable spiral. Then we have saddle type steady state or phase portrait, and then we have center type phase portrait. Now if you notice, all the equations that I have used are actually linear equations. So that means I have only one steady state, because for a linear system, the intersection of null points will be only at one position, so I will have only one steady state. Now if you have a non-linear system of OD, and that will be very common in biology as we have discussed repeatedly. For example, the predator-prey model. I have two dependent variables connected with each other using the coupled ODE, which are non-linear in nature, because you have x into y terms there also. So if I have this type of non-linear ODE, what will happen to the phase portrait? So obviously I can have multiple steady state for a non-linear system, right? So for example, in the phase portrait drawn here for the predator-prey model, I have one steady state here, I have one steady state here. The total phase portrait of the system is nothing but a combination, if you notice, combination of two phase portrait. For this first steady state here, I have a center type steady state, I have a center type phase portrait where the arrows are all moving in closed path around the steady state. Whereas for the other steady state, this is at 0, 0, it is a saddle type, so the arrows are moving away. And the total phase portrait is a combination of these two phase portraits. We can use the same technique for any other nonlinear system. We can identify the steady state by the intersection of the null lines, and then I can put grid points at equidistance and calculate dy dx to get the arrows and decide the arrowhead based on the derivatives of x and y. And what I will get is a combination of phase portrait for individual steady state. They will club together to give rise me a geometric representation of trajectory as a whole in the phase plane. Now, although we can manually draw these type of trajectories and phase portrait by hand using a paper and pen, but usually it is bit time consuming. There are many tools to do that. If you can use MATLAB, there are MATLAB codes available to draw this type of phase portrait, and they are quite easy. So let us come down to the key points that we have discussed today. For a system of ODE, the dynamic of the system is visualized by phase portrait. For a single ODE, you can draw the direction field, but for a system of ODE where you have more than one ODE, you draw a phase portrait. You choose any two dependent variable and draw the phase portrait. A phase portrait is nothing but geometric representation of the trajectories of the phase plane. So as you are representing the trajectory, the phase portrait tells me how the system evolves around the steady state. And remember, I am getting the steady state through the intersection point of the null points. To create the phase portrait, what I have to do? I have to divide the phase plane in equidistance grid point, and then I have to place arrows on each of these grid point, and the arrows will have slope equal to the derivative of one dependent variable with respect to the other one at that point. So if I am drawing the phase portrait in y versus x plot, then I will have the slope equal to dy dx. Then we have discussed that there can be different type of phase portrait for linear system. I can have stable or sink node. I can have unstable source node. I can have saddle type. I can have center. I can have stable sink or spiral. I can have source spiral. These are essentially phase portrait for individual linear system. I can consider the phase portrait for a nonlinear system as a combination of multiple phase portrait corresponding to each of the steady state. So phase portraits of a nonlinear system is nothing but combination of trajectories around each steady state. Now you have to remember that what we have discussed till now is nothing but graphical representation of the time evolution of dependent variable in a system of ODE. Here you have to draw the figure to understand the dynamics. But many times actually we want to know the dynamics purely based on mathematical analysis or algebra. So there are a good method of analysis of the dynamics and steady states of linear and nonlinear system through algebraic method. We have not discussed that because that is beyond the scope of this course. Thank you for watching this module. We will learn about different types of dynamic behaviors in the further videos.